So today I will discuss about how to localize a swarm under the water. So in Brest, what we do is we build marine robots. Here you have a sailboat robot. A sailboat robot is equipped with a sensor, such that wind sensor, GPS also. So when you have the GPS, you can measure most of the time when you have sailboats or when you have boats at the surface. Because of the GPS, you are able to measure the state of the system. For underwater robot, it's totally different. When you are under the water, you cannot use the GPS, and then you have to measure distances between buoys that are at the surface or distances between robots. He reorganized everything. No. Excuse me. No. No, I mean.
Are you using internal analysis?
Yes, of course.
So that's what it takes.
Thank you. Okay. So it is a common work with Émeric Betancourt, which is the PhD student, which is he will have his defense in next September. So when you have to localize a swarm under the water, this because the sound wave take time for communication between the robots. The problem amounts to solving nonlinear state estimation problems with delays. Delays because the sound takes time to go from one robot to another one. So I will first introduce the notion of contractors. These contractors I will introduce and I will show how you can solve some problems where the unknown belongs to R. And then I will extend this notion of contractors to deal with trajectories. So first, what is a contractor? The definition of a contractor is quite simple. You have some variables that are unknown, let's say x1 and x2, and you have an equation. So an equation or a constraint, I represent this equation like this. This equation is f of x equal to 0, for instance. But it could be an inequality. What is a contractor? A contractor takes one box as an entry and will contract this box, like this one, for instance, into a smallest one, but without removing any solution. I mean, if one point is in the initial box, it has to be in the contracted box also. So no red point should be removed by the contraction. It is the definition of a contractor. So two important properties have to be satisfied. First, a contractor contracts boxes, and then if one point is a solution, then this point should still be inside the contracted box. Of course, to compute contractors, we shall use interval analysis for this. Consider, for instance, an equation, a simple equation, such as this one. The solution, so the equation, is represented by this sine function. Here I took several boxes. If I contract all these boxes using the optimal contractor, so there is two ways to contract this box. First, the forward contraction will contract x2 only, and the backward contraction will contract x1 only. So as you can see here, if I consider this box, if I want to contract it optimally, I will remove all this x2 because all this x2, and I will have to contract all this x1 here. That's why here I obtain something like this. This box has been contracted to the empty set, this one also. Okay? So, how can I build contractors? Contractors are built using interval arithmetic. I will show you a simple example of how this can be done. Consider an equation relating three variables, x1, x2, x3. For all x1, x2, x3, we have an interval. So here, for instance, I had an interval x1, and I had an interval x2. This corresponds to this box. To contract these intervals, to generate the contracted box, how can I do? First, I rewrite the equation in three different manners, isolating each variable, x1, x2, and x3. Then, I will know that x3, for instance, x3 belongs to its domain, but also belongs to x1 plus x2, and here I use interval analysis. And why? Because x3 is equal to x1 plus x2. So I have three different manners to contract, to rewrite the equation. So I obtain three different ways to contract the box. One for x3, one for x1, one for x2. This one corresponds to the forward contraction, and these two to the backward contraction. Why? Because the initial constraints were x3, so the output, and here x1 and x2 are the input. That's why here it's forward, and these are backward. Just to show that interval arithmetic is used here to build contractors. So that's what is important to remember is what is a contractor, and to remember that interval arithmetic is a tool to build contractors. So the corresponding contractor is given here. It has three intervals as input, and we generate three contracted intervals. Once I am able to transform an equation into the contractor, I will use contractors to solve equation. And I will illustrate how this can be done using solving a simple example. Imagine that I have to solve these three equations. How can I do? I will first transform each equation into a contractor. Once I have transformed this equation into contractors, I will forget this equation and I will only use the contractors. So here, this is my three equations. The initial box will be minus infinity plus infinity for x1, for x, and minus infinity plus infinity for y. I take my first equation, for instance, the parabola, and I will contract this huge box with respect to the parabola. And all these part of the plane has been removed, and the box I now handle is this big box for corresponding to y is positive. Then I will use the contraction with respect to the hyperbola, and this part has been removed. Then I will use the contraction with respect to this equation, the line, and the white box is contracted as follows. So this has been removed. And then I have to come back to the first equation, and then to the second equation, and I obtain the empty set. It means that it is not possible to satisfy these three equations all together, And I was able to prove this using contractors only. And you should notice that I had to call C1, C2, and the three contractors several times. So that's what we call the propagation. We have to propagate the contractor. We have to call them several times until we get the fixed. So it was just to explain you that contractors is a tool that makes you possible to solve efficiently nonlinear equation in a guaranteed way. Of course, the corresponding computation are given here and there. All the time you use interval computation for the contraction. Or in fact, we have interval computation to solve our problem. Okay, so now I will try to generalize the principle of contractors. So what do we need? We need to build contractors, we need boxes. So to build boxes, a box is some kind of interval. To define interval, what do I need? I need a set, for instance, the set E, and I need some kind of order relation, like this one. Moreover, I need that this set corresponds to a lattice. So what is a lattice? A lattice is an ordered set such that if I take A and B, which belongs both to E, then the supremum and the infimum of A and B, the mean and the sum, exist and is unique. It is a lattice. Okay, so this is general, quite general. So what I want to do, I want to deal with trajectories. What is a trajectory first? A trajectory is a parametric function, is a function from R to Rn. A trajectory for, I will try to draw a trajectory here. I have here x1, x2, it corresponds to Rn, and I have the time t. So here, t. And the trajectory corresponds, associated to 1t, 1 point. But of course, most of the time, when I try to paint it, this corresponds to the trajectory. Of course, for us, it will be a trajectory of a robot, for instance. Is it a lattice? So maybe it is more easy, if you prefer, to represent the case of x which belongs to R, and here we have the trajectory because the time is here. Is it a lattice? I need to have a lattice to be able to compare two functions. For instance, I can say that the red trajectory is smaller than the blue one, and the red trajectory is higher than this one. So of course, it is an order set. Some are not comparable. For instance, if I compare the red trajectory and the black one, we cannot compare them, but it's not a problem. We just need to have a partial order relation. Now, what is the minimum of two trajectories? Let me consider, again, the time t, and here x. If I take one trajectory like this one, and one trajectory like this one, look, excuse me, then the maximum of the two of them will be, so this one will correspond to this. Well, so sometimes blue, sometimes green, this one. And the minimum is this one. So I am able to define the supremum and the infimum. So I will be able to build intervals. So this is the order relation we consider. It means that for all components and for all t, fi should be smaller than I, and the infimum and supremum as defined as expressed here in a formal function. Here, a small representation of what has been painted on the left. The set of a trajectory is a lattice, and intervals can thus be defined, and these intervals we call tubes. So a tube is an interval trajectory. An example of interval trajectory is this trajectory. For instance, I took cos t sin t, and I added an interval which depends on t. Typical interval trajectory. So this interval trajectory will be, for us, a way to represent uncertain trajectory for our robots. Of course, to be able to build contractors, I have to build the interval arithmetic. Since the intervals I consider here are tubes, because in interval trajectory, I will have to develop the tube arithmetic. What is the tube arithmetic? I can define the sum of two tubes, x and y, here. I define, I take, for instance, for all t, and I add these two intervals, and here, of course, is a classical sum of intervals. But it has to be done for all t. I can consider the shift of a tube. I take the tube, and I shift it. Okay, so I can shift it of A. Of course, it corresponds to a translation with respect to t. I can also define the composition of two tubes as follows. The composition is defined by taking, so y of t will give me a set of possible time, and I will evaluate on x, and I will obtain a new tube. And I will be able to define also the integral of a tube. So here is the integral, the primitive, which vanish for t equals 0, as follows, because of the monotony. What is important to yes?
Yes, I don't understand the third one, because if you compose a trajectory by a trajectory, even if y is as value in r, it's not possible to compose trajectories.
It depends. Of course, it has to be consistent with the dimension. Here it will work only if y has a dimension 1.
Yes.
Okay, and also here, I did not show, but you have to be able to evaluate x on an interval, which is not defined here. And in the picture here, I have shown how you evaluate on an interval a tube. For instance, here I have a tube, and the evaluation on this interval corresponds to this interval. So of course, all this have not been defined, but just to show that it is possible to deal with.
When you have good dimensions.
Yes, of course. You have to always have to have the right dimensions. Okay. And what is important to understand about the semantic is that if a tube corresponds to enclose an uncertain trajectory, the same for x and y. So what is important to have the guarantee when I define my operation is if a trajectory belongs to square x and another trajectory belongs to square y, then the sum of these two trajectories will necessarily belong to z if I define as this. So I will preserve the guarantee. Okay. So, okay, what is important to remember is that tube arithmetics will allow us to build contractors. So, how can I define contractors? For instance, I will consider, I will do exactly the same as I have done before with interval. Let me consider a differential equation with a delay. I remember that, recall that the title of the talk is to deal with delays also. So here I have a delay. I have a tube which encloses this trajectory, a tube which encloses this trajectory, and another tube which encloses U. So for our robots, U corresponds to an input, X to the state of the robot. Here, so first I decompose as follows. I will build, for instance, a new signal which is called Y, and Y corresponds to the sum of these two signals. So this is A, this is U, so A is defined as follows. So if I introduce A and Y, this simple equation corresponds to these three equations. These three equations are called primitive equations. I mean that I will have a contractor for this kind of equation, for this multiplication, for the delay, and thanks to interval tube arithmetic, I will be able to build the contractors associated with each primitive equation. If I do not have a primitive equation, then I will have to decompose into simpler constraints in order to get a primitive constraints. Okay? So how can I solve this? I will then, thanks to tube arithmetic, first contract with respect to the first equation, to the second equation, and to the last one, and I obtain the contractors which are given here. Okay, so I am able to solve in a simple and elegant way, in a guaranteed way also. I am able to solve problems involving differential equation and also dealing with delays. Okay? Tell me if you don't understand. So yeah.
Sorry to question.
Yeah?
In the prior slide, you assumed that you have a higher interval for the velocity of the derivative.
Yes?
So is it always possible?
No.
You will show.
I don't know.
Assuming that it is a...
No, sometimes it's possible, sometimes it is not possible. I can say that for our problem, with submarine robots, we are not able to measure X. So this one, most of the time, is minus infinity, plus infinity, but except when we are at the surface. But the velocity, we are able to measure it. And that is a big difference. And why we are able to measure it with a good precision? Because we have a Loc Doppler, which means because of the Doppler, you are able to know the velocity of your submarine. Okay? Okay. Now, just a simple example to illustrate how it works on a very simple situation. So, assume that X is unknown, so it belongs to a tube. And it satisfies this equation. It is periodic. If I translate by one, I obtain the same trajectory. I know this, so it is a constraint. Now, this constraint is not primitive for us because in our contractor library, we are able to contract with respect to X is a shift of Y, but not X is a shift of X itself. So I have to decompose it. How can I decompose it? Very simple way, as follows. I introduce a new signal, A, and I said the previous equation is equivalent to X is a shift of A, and X equal to A. I will have a contractor for this which corresponds to the intersection, and I will have a contractor for this which corresponds to the shift. The contractors are given as follows. So to contract from A to X, I translate A, so I do the intersection. Okay, I think you can understand. I will translate A, and I will intersect by the tube X, or I translate X, and I intersect with A to obtain A, and here just to say that X corresponds to A. This is my contractors. I will illustrate how it works in practice. In the machine, we have an infinite number of T, so we have to represent the tube as follows. Here, it corresponds to a slide, and we have many slides. Of course, we have to take some time samples, not too big, not too small. But it is a tube. Here, I have an uncertain signal, but I know that this signal is periodic, and the period is 1. Okay, as in the example I have shown. So of course, it is easy to see that my tube cannot go there, because I will not be able to be periodic, so 1 corresponds to something like this. To give you an idea after. Okay, so my tube cannot be here, and cannot be here also because, okay. So how can it work? About the propagation. This was my signal X. I translated, so here it's still the initial tube, but here it is a translated tube. So since I translate it, I will make appear new slices, and they will correspond to minus infinity plus infinity, because here I have no idea, I have no information about the signal here. That's why I have to put minus infinity plus infinity. So the previous signal tube was translated, and then I will do the intersection. And now I know that my trajectory is inside this tube. I will translate on the other direction. So I can translate left, and of course this will appear because I have no idea what was the signal here. And it was the previous signal, and I will intersect the light gray with the dark gray to obtain this. And I continue, translate, I contract, and so on, and I will converge to the dark gray tube. So the light gray was the initial tube, and now I know that my tube will be inside the dark gray tube. Okay? So it is exactly the same principle. Now, I will deal with state estimation with intertemporal measurements. I will define what it is. What is a classical state estimation problem? You have an input, okay, you have a state, so you have a first order differential equation, and for some TE correspond to measurement time, you have such an equation, okay? Okay, so the measurements you make at time t depends only of the state at time t, t1. So now we want to deal with this kind of problems because of the delays. We have a state equation corresponds to one robot, or also to many robots. Don't care. It's the same. In a mathematical point of view, one robot, many robots is the same. But what is different is that the measurements corresponds to, you have two times, T1 and T2. And I will try to explain you why it is like this. Because in our problem, you have one robot here, and one other robot which is here under the water. This one, at time T1, he sent a sound propagate, and will be received at time T2. So, of course, this one communicates, they communicate together, and with this message, he tells the other one, I am sending a ping sound at time T1. So this one knows that he received at time T2, but he knows this information about T1, but as we can understand, the measurements correspond to something which depends, because both robots are moving. At time T2, this robot will be here. Okay. And at time T1, this robot was here. Okay. So just to we have this kind of. To give you an example, we consider the mass spring problem. Just to show how it works. Mass spring problem is described by described by a nonlinear differential equation, or by this state equation. Here, the initial state is assumed to be unknown. In our problem, so this is the spring. In our problem, we need some measurement to be able to localize the mass. So how we localize? We have here an emitter which emits a sound. The sound will move in the right direction, will be reflected by the wall, will come back, and will be received by the receiver, which is at the same position at time t2. So we have some kind of state estimation problem with intertemporal measurements. And this often happens when we do some SLAM problems where the robot has to do loops. Will have such intertemporal measurements. Okay? So this corresponds to our intertemporal constraints when we do the measurements, where T1 is the time you emit, T2 the time you receive the sound. And here is my state equation. How can I solve this? I do some tube propagation, as explained before, and I will converge to a tube which encloses the trajectory. Okay. Just to illustrate the principle. Okay? Just, okay. Now I will deal with swarm localization. The swarm localization, I have many robots. So by many robots, I want to say maybe 1,000 robots or several thousand of robots. These robots are moving in the ocean. Sometimes they can communicate where they are not too far. They can send message from one robot to another, but it takes time to send a message because of the sound propagation. And each robot has a computer, and we will solve, they will try to solve the constraints propagation in a distributed way, which is not a problem for constraints propagation method. But as you can see, we have many information. We have a problem with 1,000 equations. So how will behave the contractor method for this kind of problem? In fact, they behave very well when you have redundancy, when you have much more information than what you need. So let me show you first some simulation to illustrate this. Swarm V1, for instance, this one. Oops, sorry. Okay, so here just an illustration where some robots are moving. When one robot is going to the surface, it will contract the box. And when they communicate, the robots that are at the bottom never use the GPS. If you compare to this one, they can see, they go to the surface, so they use the GPS. But these robots will never use the GPS. They can only contract their position when they are able to communicate with other robots. Okay, so it was the initialization. As you can see at the beginning, they know where they are, but they become more and more lost, and when they communicate, they contract their box. Okay? I will show you another simulation, this one, where a two-dimensional resolution for illustration, where you consider that now it takes time for the sound to go from one robot to another robot. And when it's too far, they are not able to communicate. When you can see sometimes a segment, it means that they are sufficiently close one each other so that they can communicate and exchange their distances. Okay? And also the problem which is considered here is the synchronization of the clocks. So each robot has a clock, and they are not necessarily synchronized. So they have also to solve the synchronization problem of the clocks. But, and the last problem is to show that the principle works also when you have many robots. So here there is 500 robots. You have several groups. Red robots can communicate with red robots, and so on. And when you can see a segment, it means that are sufficiently close in order to communicate. When one robot goes at the surface, it is able to use a GPS and communicate to the other via the distances. Will be able to communicate some information about their localization. And all is solved in a distributed way. Here is represented the fact that it takes time from one robot to communicate with other robots, and this has to be accounted, and it is modeled through delays. So it is a collective set estimation problem with delays. Okay, 40 minutes. I think I have finished.
Thank you very much. We have time for a few questions. Yes, please.
I noticed that these boxes and some increases in time, is that because the uncertain increase over the predicted trajectory, right?
Yes, because of course they don't use the GPS, so when they integrate the state equation, they are more and more lost.
Yeah, the question was how do you predict that trajectory? How do you estimate that increase in time?
Ah, okay. Okay, so I know. Okay, no problem. Oh, okay. So, first of all, my robots are assumed to satisfy a differential equation like this. Okay, equal f of x and u. So, what can be done if I use what I have explained here? I will use this differential equation to predict well, plus and minus. Okay. So, I will know u with a given accuracy, it's a tube. I have some information on x, I don't know, for instance, the initial condition. I will have some information on b, and I will have, for instance, some information on z. I will decompose this state equation by saying, for instance, a equal x dot, or if you prefer, x is the integral of a equal f of x u plus b. I will call the contractor for this one and for this one, and I will obtain a prediction. Did I answer your question?
Yeah.
Okay. But
So
you should know that there is more efficient technique to predict. Guaranteed efficient technique for this. Here we measure the speed. So it works. It's what is implemented, in fact, by Émeric Betancourt, which is a PhD of Émeric Betancourt I have presented here. But it is what is done by Émeric Betancourt. But for more general system, there is very efficient method to do this contraction. One which is known is, for instance, VNode, or techniques built by Nassim and many other people work with this problem. Okay? Yes?
Have you tried to develop iron with real robots?
I was waiting for this question. It's difficult to have, but here, yes, we made some tests. But here, the clock between the two robots are synchronized. So it's difficult. But we made some tests, yes. Sometimes, of course, they use a GPS when it is. So it's not totally convincing. But we have several robots like this one. We have something like 6 robots like this one, 6 Clara. And we have also other robots. But here it's an experiment with 2 robots. And also, if
So the second one is with
I don't know if it's the right video, but just to show that we made also some implementation. And also, what is important to see, if you are interested, for a scenario that what we have some a real excuse me, Okay. It is just to show what we are, the thing we are trying to do for the localization, not with one robot, but with thousands of robots, which is a cooperation with CGG Veritas, or CGG now, where they have to put many robots at the bottom of the water in order to find. I don't know why I named it. I don't know if I'm allowed to say. Maybe you can. So it is all over. You will see in the video what you are trying to.
May I ask in what depth they place the robots?
Sorry.
At what depth?
Here I think it's something like less than 100 meters.
Oh.
But we can see on the video. Think like here it looks like 30 meters.
Right.
But most of the time I think it's something like 100.
Merci.
Just to show that they have to localize all together. Sorry?
The error of the measurement that you're doing of the speed.
Of the speed, I think is something like 0.1 meter per second. Maybe less.
Maybe the robots are not moving, so I think.
You want another video where robots are moving?
No.
No, they are not.
See, yeah, okay. Rockets, yeah, okay. And then
So it's another scenario, but it's the kind of thing where.
no, because you said you measure velocity using log-tuple.
Log-tuple.
When the robots are just
Okay,
standing
so
still
speed
and-
is zero. Yeah.
So I guess we have.
No, but I have just to illustrate.
Yeah, nice, very nice video. Thanks for something to us. Okay, other questions?
Yes.
Have you looked into any application other than underwater robots?
With what?
Have you looked at any other application for this
Yeah.
other than underwater robots? So
I don't understand the last part of the sentence.
Underwater robots.
water robots.
Just the.
I think yes. We most of the time we work with marine robotics. When you are at the surface, or even when you use plane, you have the GPS. So we don't need to have a localization. But when you have indoor robotics, indoor robotics, we don't have. I think the time to communicate between robots or to measure distance is zero. So there is no intertemporal measures, except if you consider, for instance, the satellites, the GPS satellites, as robots, as a robot swarm. Then you can use this kind of technique. But I don't know. Maybe because you have to take into account relativity effect, and also the fact that the time for the wave to propagate from one satellite to another is not zero. Okay.